Welcome back, dear students. I am Razi Lohani and I am here to tell you how to obtain the equations of motion using the method of calculus. We know that the acceleration of a particle A is given by A equal to the rate of change of velocity, that is dv upon dt. If I cross multiply it, we will get dv is equal to A into dt. In this case, time t and speed or velocity v are the two variables. So integrating this equation, we get integration of dv is equal to A will be taken out as it is a constant, integration of dt. Now I will put the limits of integration. We know that if the particle starts from the velocity u and its final velocity is v, then the limits are u and v. And if we start at time t equal to 0 up to the time t equal to t, then the limits on this side will be 0 and t, and the limits of integration on this side will be u and v. Now we know the integration of dv is v. So we will write v between the limits u and v is equal to A into integration of dt is t between the limits 0 and t. This gives v, will put the values of v equal to 1, which will be equal to v, other will be equal to u, and then we will subtract. So it becomes v minus u is equal to A into the value of t will be taken as t first, then t equal to 0, and then we subtract. It will be written as therefore A into t minus 0. This gives v minus u is equal to A into t, or rearranging this equation we get v equal to u plus at. This is the first equation of motion using the method of calculus. To obtain the second equation, we start from v equal to ds upon dt, where ds is the small displacement in the time duration dt. If we cross multiply it, we get v dt is equal to ds. Now from the first equation of motion, v is equal to u plus at. So this equation becomes v u plus at dt equal to ds, or u dt plus at dt equal to ds. In this equation, the variables are t and s. U is the initial velocity, which is constant. A is the acceleration. This 2 is constant because it is uniformly accelerated motion. Now integrate this equation between the suitable limits of time and distance. So we get integration of u dt plus integration of a t dt is equal to integration ds. We start from t equal to 0, so lower limit is 0 and the upper limit is t, because we will study the particle up to the time t. So the limits of time will be 0 and t, and if we start from 0 distance, the limits of distance will be 0 and s. U is a constant, it will be taken out. So integration of dt is t. Therefore this equation becomes u into t between the limits 0 and t plus a taken out, the integration of t dt is t square upon 2. 2 is taken out, so we have t square between 0 and t equal to integration of ds is s and the limits are 0 and s. Simplifying this equation, we get u into t minus 0 plus half a into t square minus 0 square is equal to s minus 0, or u into t plus half a into t square is equal to s, that is s equal to ut plus half a t square. This is the second equation of motion. For deriving the third equation, we start from a equal to dv upon dt, or a is equal to dv upon dt into ds upon ds, where ds is the small displacement in the small time dt. I have multiplied and divided the right side by ds. On rearranging it, we get a equal to dv upon ds into ds upon dt, which gives us a equal to dv upon ds into v, where v is ds upon dt, the instantaneous velocity of the given particle. Cross multiplied, we get ads is equal to v dv. Now integrate this equation between the suitable limits. So we get a into integration of ds between the limits 0 to s equal to integration of v dv between the limits u and v, where u is the initial velocity and v is the final velocity of the particle. This gives a into integration of ds is s between the limits 0 and s equal to integration of v dv is v square upon 2, so I take half out, v square between the limits u and v. This gives a into s minus 0 equal to half into v square minus u square, which on cross multiplying gives 2as is equal to v square minus u square, or v square equal to u square plus 2as. This is the third equation of motion obtained using the method of integration. I hope you liked the video. Thank you.